Yeah. Hi everyone. So today I'm going to present the chapter 3 for the large language model book. So yeah, today's topic is about coding attention mechanisms. So since it's a relatively long topic, so I I split them into two parts. So today I'm going to present the first part. So yeah, so this overview of the book. So we are at here, attention mechanism, and attention mechanism is an important building block of large language models. So today we are going to discuss the coding a simplified self-attention mechanism, and then we will add trainable weights to the simple attention mechanisms. Yeah, and then we'll leave the rest of the topics to the next time. So before talking about the attention mechanism, so we need to know why we need attention mechanisms. So in previously, when people did machine translations, they usually used the encoder decoder recurrent neural networks, RNNs. So the figure below shows the simple framework of the RNNs. So basically, the encoder encodes the tokens into a simple hidden cell. And then the decoder will use the hidden cell to uh, translate or decode the, the sentence. So the problem with RNNs is that the decoder doesn't have the access to the earlier hidden cells. So the RNNs tend to forget the earlier context when the context is very long. So yeah, so that's why people then use the attention mechanisms. So yeah, the current mechanism used in large language model is called self-attention mechanism. So it's a mechanism that allows each position in the input sequence to attend all positions in the same sequence when computing the representation of the sequence. Yeah, so why it's called self-attention is because it measure the relationship between the tokens in the sequence, in the same sequence. So yeah, so let's begin to code our simple self-attention mechanism without any trainable weights. So using so we have a sentence here, your journey step starts from blah, blah, step, and then we'll use the second token as the example. So it's X2, second one, which is journey. So the goal is um, to construct the context vector for journey. So Z represents the context vector, Z2, and X2 is the token of journey. So basically, this mechanism weight the input tokens using the attention weights, and then we'll sum them up to construct the context vector. So the first step is to derive the dot product between the input token x2 with all the tokens in the sentence. So for W21 is the dot product between the x2 and x1. So yeah, so on and so forth. We can calculate other dot products for between x2 and other tokens. So a quick review for the dot products. So it quantifies how much two vectors are aligned. So it represents the similarity between two vectors. So a higher dot product indicates a greater similarity between the vectors. So mathematically, it is the sum of the element-wise multiplications in 1D tensor. So yeah, the step 2. So after we obtain the dot products, we will normalize them.
So 1 second. So
Okay.
in your explanation for the dot product, if we look at the next slide,
Yep.
so we would find 1.4 and 1.4 are the most related. So journey is related to
Yes.
start. Okay.
So yeah, and we can see that for W22, because this is the dot product between itself, so it's obviously the most relevant one, so it's very large. So yeah, after we obtain the dot product for our with respect to the second token, we'll normalize them using the softmax function. So that the attention weights, the summation of attention weights will be 1. So yeah, so step 3 will be what we just mentioned before. We weighted the tokens with our attention weights and then sum them up to obtain the final context vector for the second token journey. So yeah, so to have a better understanding, we can go into the code now. Okay, so make it smaller. So yeah, this cell has the input for input sentence. Your journey starts with 1 step. So we focus on the second one, which is journey. So we can run this one.
I'm not seeing anything. Are people seeing the screen?
You didn't see?
I'm seeing a notebook and also your slides. So they're
Yeah,
like
so
side by side.
I'm talking about the notebook now.
Oh, I may have to leave and come back. I don't know why. I'm seeing blank.
I will share it again. Weird.
So that computer view is Franca.
Maybe just share one screen only. One window only.
Yeah.
No, the desktop. Yeah.
Okay. Then we won't see the. Yeah, it's weird. I don't know why he does it. Oh, okay, cool. So can you see it now? Okay. So yeah. So first we initialize our input, like your journey starts with one step, and we focus on the second one now. And then, yeah, so the query here is input one, so it's this one, journey. So basically, we multiply the elements between the query and other tokens in the sentence. So we will get these numbers, which is what we saw in the example in the slide. So yeah, it takes the dot products between the query and other tokens in the sentence. So yeah, and next cell show the how torch dot works. So it compute the first value for us. So you can see that so it basically is doing the element-wise multiplication and then sum them up. So we'll get the number which is the same by using torch dot here. Yeah, so and then yeah, we can skip this one, and then this cell is defining the softmax function, a naive one for us. So it will normalize the dot products. And then we can see that the summation of the attention weights is 1 after we normalize the attention scores.
I think your screen is.
Yeah, your screen is frozen.
Yeah, I'll change my just character. So can you see the screen now?
Yes, I can see the notebook, chapter 3.
Great. So we are at the softmax here. So we can see that the summation of the attention weight is 1 after we fed the dot products into the softmax functions. Yeah, so yeah, the next step is to use this attention weights to weight our input tokens, which is what it is doing in this cell, and then sum them up to construct the final context vector for the token 2, x2. And then we can do the same for all other tokens beside the second token. So we can construct the attention matrix for all the tokens. Yeah, and then and all these operations can be expressed using simple matrix multiplications. So it's very clean here. We only need one line to obtain the attention matrix. We don't need a nested for loop for doing this. Yeah, so we just conduct the metric multiplication between inputs and the transpose of the inputs, and we can obtain the attention scores. And then we can pass it to the softmax functions to normalize them. Yeah. So this is just a double check that the summation of the second row is 1. And then the final step can also be done by the matrix multiplication. So we multiply the attention weights with the input and then get all the context vectors for all the tokens in the sentence. So let me go back to the slides now. Slides here. So yeah, so now we will add the trainable weights into our picture. So they say like adding the trainable weights can create good context vectors. So the concept is very similar, but the difference is that we first transform our input vectors into 3 new vectors, which is query, key, and values. So it's transformed by the trainable weights, WQ for query, WK for key, and WB for values. So so in this case, we are still using the second token x the example. So so in this case, we don't need query for x1 and other tokens except x2. So why we need key, query, and value? So the concept is borrowed from the information retrieval and database. So yeah, so where similar concepts are used to store, search, and retrieve information. So query represent the current item the model focuses on or try to understand. And key is the indices. Keys are the indices for the items, and values are the actual contents or representation of the input items. So yeah, the second step is to compute the dot product between the query of token 2 with the keys of other tokens. So we can obtain the attention score here using the dot products, similar to the simple attention mechanisms. Yeah, and the next step is the same. We pass the attention score into the softmax function to obtain the attention weight. Yeah, and next step is to weight the value with the attention weight and then sum them up to compute the context vector. Yeah. So the main difference is with between this mechanism and the simple one is the trainable weight, the WK, QK, and V. So these weights will be updated during the training. So similarly, we can compute all the context vectors for all the tokens. Yeah. So Yeah, let me go back to the code. So we already know how it works for dot products and matrix multiplication. So we can go directly into the class they create to see how this works. So in this class, it initializes 3 ways, WQ, WK, and WV. And then we will transform our input vectors into keys, query, and values using the ways we just initialized. And then we can compute the attention score using the matrix multiplications between the query and keys. And then we'll normalize them with the softmax functions. And then finally, we can weight our weight the values with the attention weights to construct the final context vectors. So this is a naive class. So the author further improved it using the linear layer in PyTorch package. So the linear layer basically replaces the initialization of the parameters and also the matrix multiplications. Yeah. So to obtain the keys, we just need to feed the key query and values. We just need to feed the input tokens to the linear layers. So yeah, and the next will be the same. So finally, you can compute our context vectors. So I think that's pretty much for today's presentation. So yes, do you have any
Great.
questions? Yeah.
Questions, comments?
I guess I have one.
Mhm.
In the book, when they're ever showing the examples of the cosine about the similarity, I think one of the similarity matrices, I was expecting the diagonal to just be ones because it's comparing the same input to itself. But when they discuss it, they don't do like any of the scaling you do with the dot product so that it gives you a value between -1 to 1. Do they give a reason why they just avoid doing that, or?
I am not sure. So you are saying that the dot product, the difference between dot product and cosine similarity?
Well, so if you're doing the dot product for just similarity,
Yeah.
I figured you're doing the similarity so that it goes from like, let's say -1 to 1. But in their examples, it goes to like 1.4 and other values. So it's not.
So if you pull up the like the chart where even on your slides,
Yep.
I think this is what Ramon is trying to ask. Where yeah, keep going.
So yeah, in the case they didn't normalize it by the length of the vector b. So it won't be scale into -1 and 1. Yeah, I think.
But maybe that's because they do that with the softmax on the next step, right?
Yeah.
But I don't know why.
Yeah, so I believe if you normalize it, it still works, but it just takes an additional step to achieve that.
I think that may be because that the normal bay is actually a common factor. So that when we are doing the softmax, when we're getting the weights, this common factor actually gets out. So that's why we don't waste the computational power on this.
Yeah.
Okay, great. Yeah, that's good to know then.
Any other questions or comments? Okay. Frank, what did you learn from this
So it's
by
the
preparing
like
on part one?
so I learned how so I get to appreciate how elegant this is. Like we just need a matrix multiplication to replace all the like summation and multiplication, element-wise multiplications. I think it's very cool.
Okay. Okay. Wes, did you have a chance to read or anything new that you observed?
Regarding the club, uh, so like haven't got any chance to gotten a chance to anything new, but like I'm really enjoying this right now because understanding because I'm familiar with like matrix multiplication and like all the mathematical stuff, but like putting all together and understanding like how like what's behind the LLMs, like what's the math behind the LLM. So it clears a lot of things.
Awesome. Theo?
Yeah. New things I learned. With this book, as I mentioned previously, is like breaks it down really easily for us to understand, and then how it takes us step by step from taking like a naive model and then building on top of it, and then showing the actual in production code. Like for example, instead of using torch parameters, and then it's translated all directly to the torch linear layers. And then another thing I learned is that regarding like, because it's step by step, then we understand like how to include weights into the basic self-attention model, and then breaking it down into the query key values and how the operations work. It's really explained really well. And also from discussion, like for example, just like right now, Ramon's question, and that's also like something new that I learned regarding the, you don't have to perform like the normalization at this step because it reduces the computation power. So that's another thing that I learned.
Okay. Wenya?
I also think that the tutorial is very great because it's pretty detailed, but like regarding to the computational efficiency of this matrix, I actually think that because now the data base is very small, it is 6 by 3, so that we can do the tension weights and directly do the matrix multiplication. But since like we know that this matrix is actually symmetric because in dot product, the W21 equals to W12 as dot product ignores the order. So I think like when we're dealing with pretty large databases, then we can actually solve like the upper triangular entries or the lower triangular entries because that actually represents the whole matrix. So in that case, we can save half of the time efficiency and half of the space efficiency.
Cool.
Okay. Okay. Sorry, Amirali?
Hi. Thank you, Frank, for the presentation. I think this chapter really made it simple to understand the attention mechanism as we talked about in chapter 1. And the really fun thing was that I usually use torch.mat multiplication for multiplication of matrices, but I really was surprised that we can use at sign for doing math multiplication. And I think that was cool.
Ramon?
Yeah, it was nice to go through the implementations. The next half of the chapter where they do the multiple mechanisms and the causal attention are probably the nicer parts because I've only just read about them but haven't like tried using them. So I think maybe I'll just try running them a little bit just to get more familiar.
Yeah, go.
I had a pleasure to repeat all these materials because I already read a lot of articles about attention
3?
because it was a really complicated material to me to understand what is attention, not from the code, like how to implement it, but understand how it works and why all this key values, key and queries are used to, and how to understand the principles of working. So it was good that to listen again about this. Thank you.
Awesome. Alex, how are you? I know you're just joining the book club for the first time. Hopefully you're enjoying your summer away.
Yeah, I'm very good. It's actually very funny that I joined this meeting because I'm like in the middle of trying to figure out some attention for epigenomic tracks, like trying to make my own model using some attention mechanism. So this actually was incredibly helpful. And I've just separately been trying to learn about this on my own. So this was actually like just by chance incredibly helpful for me with some syntax things and also just like the actual workings of the mechanism will definitely help out. Yeah, thank you, Frank.
Awesome. Yeah, so I mean, great job, Frank. And I do, when I selected this book, I hadn't read it, and but Sebastian is a very, very strong educator, and I think you're seeing that, right, from how he writes, how he does the work, and this is a book that I think the first time Amirali presented, and it's like, oh yeah, I mean, who's running a big LLM project right now, and it's like, oh, this was a very intimidating book for me to read, and he did a fantastic job. I think for me, it was just understanding the sort of like the framing of when I read this book, like, can I make sense of it? And that's the danger of machine learning, especially as more data sets are going to come out, that you lose the basics. And you don't need to be bogged down with the basics that you cannot keep up with the new technologies. But if you have a rock solid foundation, then it's going to allow you to maybe not develop the next architecture, but understand where you can apply it and where you cannot apply it. So this book continues to be very very much to my learning style about understanding, oh, okay, this is the attention mechanism. Okay, I can understand what this is happening. And so again, I encourage everyone to go back, as you go to the gym or walk or travel, just play back the other chapters or just browse the book again, because I think things are going to solidify when you understand, okay, this is what this means. And, when you go back. And so that's just my encouragement to keep learning, but I look forward to the second part of the book. Cool. Awesomeness. Okay, so well, we'll end early and we'll see you next week. Thank you.
Thank you.
Thank you. Take care.
Bye.
Bye-bye.